Hey everyone, welcome back to Education is Life, your go-to channel for unlocking the wonders of learning. It is me, Joe Edgo, and today we're diving into Lesson 6 of the Arduino UNO R4 Minima, Ultimate Training Series, focusing on analog to digital conversion, highlighting bits, bytes, and binary numbers. In this lesson, you'll fully understand how binary numbers are being used in digital devices. Through the use of a potentiometer, you'll have a good grasp of how analog signals, typically analog voltages, are symbolized in digital form. Finally, you'll learn how to write a program using while loop construct to convert decimal numbers into binary numbers easily. As always, I'd like to extend my sincere gratitude to SunFounder for sponsoring this course and enabling everyone, especially beginners, to embark on this comprehensive educational adventure. SunFounder has kindly donated this Arduino UNO R4 Minima Ultimate Sensor Kit, which will be our constant companion throughout this series. So, for those who are still searching for resources to aid them in their journey with the new Arduino UNO R4, I recommend you give this one a look. This is available on the SunFounder website as well as on Amazon. The links are in the description below. So now, let's begin. For this session, you need the following materials: a 10 kilo ohm potentiometer and a 1 kilo ohm resistor. However, if you have your SunFounder kit, you can simply use the potentiometer module. Here, it is labeled as rotation sensor. You'll also need 8 LEDs with 8 1 kilo ohm current limiting resistors, a breadboard, some connecting wires, and your Arduino UNO R4 Minima. In our previous lesson, you learned how digital input pins work in Arduino UNO. You discovered how easy it is to use push-button switches in your projects when working with digital inputs. Particularly, you've seen that when a pin is configured as digital input, the Arduino UNO board will report high if it reads a voltage of about 3 to 5 volts, and it will report low if it reads a lower voltage somewhat close to 0 volts. In digital circuits, we simply deal with two states: high or low, true or false, on or off, logic 1 or logic 0. Digital circuits use transistors to form logic gates in order to perform Boolean logic. The microprocessors inside your computers, smartphones, microcontrollers, and other computing chips are digital circuits designed to operate in the digital domain. Depending on the digital logic family of the microchip you're using, these logic levels of high and low slightly vary. For example, TTL or transistor-transistor logic is one of the widely used digital logic families in the design of integrated circuits. The acceptable input voltage range for a TTL device to be considered high or logic 1 is from 2 to 5 volts. And to be considered as low or logic 0, it should be within the range of 0.8 to 0 volts. Digital circuits use a binary system for digital signaling, a system that assigns only two different logic levels for two different voltages: a high voltage that is typically 5 volts, 3.3 volts, or 1.8 volts, and a low voltage that is usually 0 volts. However, you must understand that we live in an analog world in which practically everything we see, hear, taste, feel, and smell is analog. There are infinite colors that are indistinguishable from our sight, infinite tones that we can hear, and countless fragrances that we can smell. So, when we work on an electronic project like this, where it needs to interact with the real world, we have to deal with both digital and analog signals. Understanding how real-world analog signals are converted and represented in digital form is very important. Microcontrollers like Arduino UNO, although considered digital, often have internal circuitry that allows them to interact with analog circuitry. In Arduino, when we talk of analog signals, just think of them as a voltage that is changing over time. Arduino UNO has 6 analog to digital converter pins that can be used to connect to a variety of analog sensors to read analog voltage. To demonstrate this concept, let's start with a potentiometer. Potentiometers come in many shapes and sizes and are used in many parts of your daily life. The volume setting on your car radio is a very common example. This is the symbol for a potentiometer. It is a manually adjustable resistor with 3 terminals. Both terminal ends or fixed ends are connected to a resistive element, and the middle terminal or the variable end is connected to an adjustable wiper. So, how exactly does it work? The resistance between the outer two pins, pin 1 and pin 3, will not change. For example, since we are using a 10 kilo ohm potentiometer, the resistance between pins 1 and 3 will always be 10 kilo ohms regardless of the wiper position. Now, the control of a potentiometer is in the middle terminal, pin 2, whose resistance varies depending on the potentiometer's wiper position. Think of a potentiometer as a device containing two independent resistors, R1 and R2, that always sum to a total resistance, which is the potentiometer's total resistance value, in this case, 10 kilo ohms. Notice that as I move the wiper position in a clockwise direction or to the right, R1 resistance increases as R2 resistance decreases. Similarly, I can measure the R2 resistance, and as I move the wiper position in a counterclockwise direction or to the left, R2 resistance increases as R1 resistance decreases. There are two common ways to use a potentiometer in your circuit. It can work as either a rheostat, just a variable resistor, or as a voltage divider. To use a potentiometer as a rheostat, only two terminals are required, the middle pin and one outer pin. You can use any of the two fixed end terminals, pin 1 or pin 3. To illustrate this, let's implement this circuit diagram. Using an LED, I'll connect its positive terminal to a 1 kilo ohm resistor in series. And then, I'll connect the variable terminal or pin 2 of the potentiometer in series with the 1 kilo ohm resistor. To complete the circuit, I'll connect the 5-volt source of the Arduino UNO board to one of the fixed end terminals of the potentiometer, say pin 1. Then, the ground of the board to the negative terminal of the LED. So now, using it as a variable resistor, the position of the wiper determines how much resistance the potentiometer is imposing on the circuit. As I rotate the knob clockwise, thereby changing the wiper position, we can get a value from 0 to 10 kilo ohm resistance at R1. In effect, the LED gets dimmer as the resistance gets higher, reaching 10 kilo ohms. Since we also have a 1 kilo ohm resistor here in series, this makes a total of 11 kilo ohms. On the other hand, the LED gets brighter as the resistance gets lower toward 0 ohm. That is the reason why I placed a 1 kilo ohm resistor here in series, so that when the variable resistor reaches 0 ohm, we still have a minimum resistance of 1 kilo ohm to protect our LED from burning out. We can also use the other fixed end terminal, pin 3, instead of pin 1, and it will have the same effect. The only difference is the orientation of the knob with respect to 0 ohm and 10 kilo ohm. Here, since we are now referencing R2, as I turn the knob clockwise, the resistance on R2 decreases, thus the LED gets brighter. And as I turn the wiper counterclockwise, R2 resistance increases and the LED gets dimmer. Now, to use the potentiometer as a voltage divider, all three terminals are required. Here, voltage must be applied across the outer terminals, pin 1 and pin 3. For this illustration, I'll connect one of the outer pins, pin 3, to the 5-volt source or VCC, and the other outer pin, pin 1, to the ground or 0 volts. Here, the center pin acts as the voltage output. When a potentiometer is used as a voltage divider, the wiper position determines the value of the output voltage in the middle pin. But how? This is the equivalent circuit diagram when you use a potentiometer this way. It's like having two resistors in series, and this in-between junction represents the center pin that is used to measure the voltage across the resistors. In case you would like to refresh your knowledge of the voltage divider circuit, please refer to the video links below. I'll use a voltmeter for you to see how the circuit divides the 5-volt source depending on the ratio of the two resistances as I change the wiper position. As I turn the knob toward the 5-volt terminal of the potentiometer, the output voltage also increases. And as I turn the knob toward the terminal connected to the ground, the output voltage decreases. Understanding this simple concept is very important for you to grasp how microcontrollers such as Arduino UNO read analog signals, and then eventually interpret them in your code. These analog signals, in the form of voltage that is changing over time, could be coming from different sensors. And this is what we are going to explore in many of our future lessons, with the help of this SunFounder Ultimate Sensor Kit. In place of the potentiometer circuit, you can also use the rotation sensor included in the kit. This sensor uses a 10 kilo-ohm potentiometer and a 2.5 kilo-ohm resistor in series with a middle pin. However, please note that this module already has a pin-out arrangement of ground, VCC, and out from left to right for easy connection. So, I'll replace this potentiometer with the SunFounder Rotation Sensor, and it is expected to perform the same. Now, to read an analog signal from Arduino UNO, we can use any of the 6 analog input pins labeled A0 through A5. If we choose A0, all we have to do is to connect the output voltage pin of the rotation sensor to pin A0 of the Arduino UNO. In our sketch, we define the sensor pin A0. Then, in the setup function, we don't need to set the pin mode when reading a value from an analog pin. Here, we just have to initialize the serial monitor for displaying the analog to digital readings later. Inside the loop function, we can simply read the analog value from pin A0 using the analogRead function and pass the analog pin A0 as an argument. This function measures the analog voltage from 0 to 5 volts at pin A0, converts it into a digital value, and returns it as an integer. So, I'll create an int-type variable called ADC value and use it to assign the return value of this function. And then, using the serial.print function, I'll display the text ADC value in decimal. Here, I use the print function instead of println. It means that the cursor remains on the same line and does not move to a new line. It is because on the same line, I will print the actual ADC value before moving to the next line. Let's have a short delay of 50 milliseconds before it loops back and reads again. Now, I'll upload the code and see what happens. Notice that as I rotate the knob clockwise, the analogRead function returns a digital value from 0 all the way up to 1023. This is the converted digital value from the analog voltage ranging from 0 to 5 volts. So, this analogRead function simply maps the input voltages from 0 to 5 volts at pin A0 into integer values from 0 to 1023. But why 0 to 1023? Well, this range of values depends on the resolution of the analog to digital converters used by the Arduino board. The default resolution for the Arduino UNO R4 Minima is 10 bits, but it supports up to a maximum of 14 bits resolution. So, what is a bit and what is a resolution? A bit is short for binary digit. It is the smallest unit of data that can be represented on a digital computing device. It's a single unit of information with a value of either 1 or 0. So, if we only have 1 bit to represent something in the real world, we only have 2 possible outcomes, either 1 or 0. If it is a light, it could be bright or dim. If it is a sound, it could be loud or quiet. If it is a texture, it could be rough or smooth. If it is an analog voltage, it could be 5 volts or 0 volts. There's nothing in between, no variations, there are no levels of granularity. But then again, in an analog world, there are infinite possible values of sounds, colors, textures, temperatures, and everything. And using only 1 bit to represent something from an analog world would be inaccurate. That is why increasing the number of bits to represent analog signals would increase the precision of the measured values. For example, instead of just 1 bit, if we use 2 bits to represent the analog voltages from 0 to 5 volts, we will have 4 possible outcomes or combinations. 0, 0 would represent 0 volts, 0, 1 would represent 1.67 volts, 1, 0 would represent 3.33 volts, and 1, 1 would represent 5 volts. If we use 4 bits to represent the analog voltages between 0 to 5 volts, we will have 16 possible combinations, which means more ways to represent information. That is 0, 0, 0, 0 to 1, 1, 1, 1. And this is how we count in a binary or base 2 number system. Similar to how we count on a base 10 or decimal number system that we have been very accustomed to since grade school. The base, also called radix, determines how many different symbols are required to represent a number system. In the decimal number system, we've got 10 numeral representations of 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And if we exceed 10 counts, meaning we run out of symbols after 9, then we've got to reset all the digits to the right to 0 and increase the left digit by 1. The same thing happens when we reach 99. These 2 digits reset to 00 and increments the third digit by 1, making it 100 or 100. And it goes on. Now, for the binary number system, we only have 2 numeral representations of 0 and 1. It means that after 1, it resets to 0 and increments the left binary digit by 1, making it 10, and then followed by 11. Again, since we ran out of symbols, we reset both bits to 00 and increase the left bit by 1, making it 100. And the counting goes on. Thus, if we have 4 bits, that is base 2 raised to 4 bits, giving us 16 counts from 0000 up to 1111. And this is a direct equivalent of decimal numbers 0 to 15. For example, 9 in the decimal number system is equal to 1001 in the binary number system. So, as you noticed, as we increase the number of bits to represent an analog value, the more precise it can get. And this is exponential. For every additional bit, the number of discrete counts or levels to represent analog signals doubles, such that if we have 5 bits, we have 32 discrete levels. For 6 bits, we have 64 discrete levels. For 7 bits, we have 128 discrete levels. And for 8 bits, we have 256 discrete levels. That is 2 raised to the number of bits. With this, we can define that the number of bits an analog to digital converter uses to digitize an analog input signal is called resolution. Resolution determines the precision of a measurement. The greater the ADC resolution, the more precise the measurement values. In computing terms, a group of 8 bits is called a byte. Historically, a byte is considered the smallest addressable unit of memory in many computer system architectures because it is used to encode a single non-Unicode character. A byte is used to represent a single character like A, B, or C. Thus, 8 bits can only represent up to 256 characters at most. So, going back, Arduino UNO R4 has a default ADC resolution of 10 bits. That is 2 raised to 10, which means a 10-bit ADC resolution would give us 1024 different discrete levels. This is symbolized in a decimal number system from 0 to 1023. Now, if we want to know the analog voltages that correspond to each of these 0 to 1023 discrete levels, we can have a simple computation in our program that maps the values being read. First, I'll declare a local float variable, analog volts, then map the ADC value being read by multiplying 5.0 volts. This is the maximum voltage. And by dividing 1023, this is the maximum ADC value. And that's it. Then, using the serial.print method, I'll print analog input voltage, colon, and on the same line, I'll print the computed analog voltage with 4 decimal places. Now, I'll upload the code and see what happens. As you can see, the analog input voltage ranging from 0 up to 5 volts is displayed together with the converted ADC value in digital form. For example, an analog value of 1.2463 volts is equal to 255 in decimal when using a 10-bit resolution ADC. Note that this precision can be changed when using a different resolution. Although the default is 10 bits, we can set it as high as 14 bits. And to do this, let's define another constant, resolution, with a value of 12. So 2 raised to 12, which means that we can have 4096 possible discrete levels to represent 0 to 5 volts analog signals. That is 0 to 4095. Here, instead of hard-coding 4095, when we compute the analog volts, I'll simply declare an int variable, maxval, and compute the maximum decimal number depending on the resolution. That is 2 raised to the number of bits minus 1. For that, I'll use the pow function. The first parameter is the base, and the second parameter is the exponent. Then, subtract the answer by 1. It is like saying 2 raised to 12 equals 4096 minus 1 equals 4095. Now, in the setup function, I'll simply call the analogRead resolution and pass in the desired resolution. Also, I'll change this hard-coded value of 1023 and replace it with maxval variable. And that's it. I'll upload the code and see what happens. As you noticed, using a 12-bit resolution is more sensitive in reading slight variations in the input voltage. An input voltage of 1.2491, for example, is converted as 1023 in decimal instead of 255, while 5 volts is converted as 4095 in decimal. Now, aside from this, we can also display the converted binary data. To do this, first I'll declare another local variable of type uint8_t, bit count, and assign the current resolution. Well, basically, this is the same as of type byte. It is shorthand for unsigned integer of 8-bit length. You can use the byte type if you want to. And then, I'll print ADC value in binary. Now, there is a function called bitRead, and what it does is that it reads the bit of a variable. This function accepts two parameters. The first one is the number to be read, so it will read the ADC value. The second one is the bit position from which to read. So, for example, if we have a decimal number 2023, the equivalent 12-bit binary number is 0111-1110-0111. If you are not that familiar with binary to decimal conversion and vice versa, you can simply reference this table showing the power of 2 geometric sequence. That is 1248, 16, 32, 64, 128, 256, 512, 1024, 2048, and so on if you have more than 12 bits. Ideally, you'll be able to convert fast if you memorize the sequence. All you have to do is sum up all the values that correspond to logic 1 and ignore the values that correspond to logic 0. So, 1024 plus 512 plus 256 plus 128 plus 64 plus 32 plus 4 plus 2 plus 1 is equal to 2023. As simple as that. Here, the least significant bit is the rightmost bit, denoted as bit 0, and the most significant bit is the leftmost bit, denoted as bit 11. So, if I call the bitRead function and pass in 2023 and 11, it should return 0. And if I call the bitRead function and pass in 2023 and 10, it should return 1. Although we can call this bitRead function 12 times to display bit 11 down to bit 0, that's not a very efficient way of coding it. So, to efficiently display all these bits at once, we need to perform a loop. We have several looping statements available in C language. The first that we are going to use is the while loop. Similar to an if statement, a while loop evaluates a condition inside this parenthesis. However, in a while loop, while the condition is true, the code inside the while block is performed and then loops back. So, the algorithm to accomplish this is to start from bit 11 and then display each bit one by one on the same line until we reach bit 0. So, I'll have a condition that checks if bit count is still greater than 0. At the start, this is 12 greater than 0, which is true. Thus, it performs the code inside the loop. Now, inside the loop, I'll decrease bit count by 1. This becomes 11. And then I'll print the return value of the bitRead function. Here, I'll use the bit count as the second parameter. So, during the first iteration, bit 11 gets displayed. And then, it loops back to perform the same operation. But for the second iteration, bit 10 gets displayed. So, this while loop gets to be executed 12 times until bit 0 is displayed. Let's upload the code and see if it works. And as you can see, it works perfectly. Now, let's test using a different resolution, a smaller resolution of 8-bit. So, in this illustration, you can see how an analog voltage from 0 to 5 volts is converted into an 8-bit digital value from 0 to 255. For your challenge activity, I want you to implement a similar circuit connection but with an additional 8 LEDs connected at pins 0 to 7. Improve this program by sending the 8-bit binary value to the 8 LEDs aside from just displaying it on the serial monitor. This is not hard, but it is a bit tricky as compared to the previous challenge activities. As a hint, you'll have to modify the while loop to accomplish this challenge. Again, thank you so much for joining me in this lesson on analog to digital conversion, highlighting bits, bytes, and binary numbers. For our succeeding lessons, we'll explore more sensors and digital to analog converters. If you found this lesson enlightening, don't forget to hit the like button, subscribe for more knowledge-packed sessions, and ring the bell to stay updated. So, keep learning, keep experimenting, and always remember, education is life. See you in our next lesson. Happy coding!